for you to go sort of see how what we learnt in this course carries forward to current day research and things like that, but the steps will be fairly slow, and there are some beautiful ideas which need quantum field theory, but I think I can tell you the words and the pictures which go with it, so that you get an idea of where these things fit with quantum field theory, quantum mechanics, so on and so forth, and even current day research. Okay. So the one title for this lecture could be soliton democracy. This is just an adaptation of a title of a paper by Townsend, which is titled P-brain democracy, and that talks about democracy among p-brains. Similarly, we will talk about democracy among solitons. So the thing is, what we have seen is that in classical field theories, so there are solitons and there are what we will call elementary excitations. Okay, so the idea of elementary excitations is that suppose I have a scalar field we are kind of told that if you go ahead and go to quantum field theory, the normal elementary excitations or the low energy excitations would be excitations of the scalar field, which would be related to scalar particles. Okay. And so this is something which we need quantum field theory, but at least we can go ahead and look at these things. But solitons do not seem to come into that sort of a thing. They look like they are lumps, as Coleman likes to call it. They are classical lumps of energy. Okay, and we have seen, for instance, the king soliton, it could be fairly localized. So but these also behave as particles. Okay, and you can do things like, can I try to quantize this thing, like you quantize particles in quantum mechanics, you can talk of quantum mechanics of such particles. Okay, so there is a sense in which you could do this, but typically these things are massive, very this thing, and they are not low energy excitations. So really, whenever you talk of excitations of a field theory from a classical field theory to the quantum field theory limit, you actually thinking of these scalar particles. Okay, so the democracy which I am going to discuss today is going to tell you this picture of separating these two things out is very naive. There is a sense in which these also have to be taken into account, and for instance, in the path integral approach you will see there are reasons you should look at configurations which are related to solitons, but I am saying something more dramatic or different. What I am saying is that there could be an alternate description where these solitons are elementary excitations of some other theory, while these scalar particles are solitons of that theory. That could happen, and we are going to see an example of that. Okay. So in other words, there can be new variables or new fields for which the solitons are the elementary excitations, but still there is a problem. The problem is that like I said, these things tend to be very heavy. So there must be a sense in which they can become light. So if you look at typically, what we will see is that typically soliton masses, which is the same as the energy, tend to be proportional to some coupling. They go like 1 by E square or 1 by E, and we are told that quantum field theory requires this E to be small. That is where perturbative quantum field theory works. So this is some bookkeeping parameter, you are doing some Taylor expansion or whatever, where E square or E square h bar or alpha prime is a small number, and then you can see that 1 by E square is a fairly large number. That is why it is massive, but if E is a parameter in your theory, I can ask what happens if E becomes very, very large. Then clearly you can see that if this formula does not change, if you naively look at this formula, and let us say this formula does not change for large E, you can see that the soliton mass becomes lighter and lighter. And so there can be a regime where where E, of course your perturbative methods in quantum field theory die down, but there could be I mean these you can see that these become it becomes very cheap to create these solitons and destroy these solitons. Okay, and that's so really it's I should say soliton elementary particle democracy in some sense. So what we will do today is to see 3 different examples. I mean I may get to the third, otherwise I will do it next lecture. So the idea here is that suppose we have 2 different theories which have the following property, that the solitons of say let us call this A, solitons of theory A become the elementary particles of some other theory and vice versa. We will call that a duality. Okay, so we will we will see 3 examples of what I will call duality. And they are all what are called strong weak duality, S duality. Okay, so this is the kind of thing, one of them. So you can see what we are saying here is that E becoming large is strong coupling. Okay, so there is a coupling constant of your theory. So the first example is actually the Erising model. So you are told that this is a field theory with a variable sigma, and let us say I will just deliberately use continuum index, but you could think of it on a lattice where the x takes values in some lattice which belongs to say plus or minus 1. Okay, and so we know that for instance the tour de force, which is the 2D Erising model, can be solved exactly, you are told. One D and 2D, and then you are told that the 3D Erising model is the computation of the ground state energy is something like NP hard or whatever. Okay, so but what I want to tell you is that this model at low temperatures it has the following behavior at low temperature. So now the analog of the parameter E is going to be temperature. Okay, so it is something which I can control, I can change the temperature. At low temperature we have an ordered phase, and at high temperature all the up and down everything is this thing, so you have a disordered phase. So in the ordered phase sigma, the expectation value, the average. So this is an example by the way not from field theory but from statistical mechanics, but does not matter, it is also a field theory, and in this phase sigma equal to 0. And the argument for a phase transition is done in the following way, is that there is another set of variables you can construct which I will call mu of x. These are non-local in this theory, non-local in terms of sigma of x. Okay, I am not going to give the constructions. This you can go and look at it in books, in StatMech books, maybe some of them will have it. So this variable I will call this the disorder variable, for want of better reason, and you can show that you can rewrite the whole Erising model in terms of these variables mu, and mu again takes only values plus or minus 1, and it is complicated to write it in terms of sigmas. It has it's non-local in the sense that to describe it you need, there will be a tail if you wish, starting from some infinite point down to this thing, you have to write that. So it will be, it's not some localized function of sigma of x, okay, it is non-local in that sense, and but nevertheless I mean that is okay. So but this also takes values plus or minus 1, and the nice thing is that you can ask what happens you can show that you can rewrite the Hamiltonian if you wish of the Ising model in terms of the mu variables, and what you will discover is that the temperature gets flipped, okay. So mu variables, it is another Ising model in disorder variables, okay, and roughly speaking T goes to with temperature 1 by T, okay. So now you can see that large T, this is a high T becomes low T for the disorder model, Ising model, and it will be in the disordered phase will be when the disorder parameter is ordered. It's kind of confusing, okay. So I'll just write something here, and obviously this is like high temperature for this. In fact, anybody who has solved the Ising model will see that you get the expression, there are two betas which come, beta and a beta tilde, which are related by precisely this kind of thing, okay. And so the thing is the point, so that there exists a phase transition, you can see is that what is happening is that these variables go to the other variables, okay. So this is an example of a model which is strong weak dual. I mean strong here means high and low temperature expansions get exchanged, and it is self dual because it maps to a model of the same kind. So this is an example of what I said, theory A, theory B, okay. And I also said the variables are not going to be so simple to write. The solitons are not I mean they are not localized objects, they have some spread, etc. So they, in terms of these variables it will be pretty complicated, okay. So this is the first example, and the second one is a proper field theory. So it is a 1 plus 1 dimensional field theory, okay, and it is called the Sine-Gordon model. I guess this name was given by Finkelstein in casual conversation with his student Rubinstein, but and he never expected Rubinstein to go ahead use that name in the paper, okay. And but he said that it was too late to take Rubinstein to task because Rubinstein had graduated. So it's a I will write a whole bunch of things. Okay, so hopefully there are no errors here. Yeah, I think this is fine. Now I will check for some factors I need to put. Yeah, that's correct. Okay, so the reason this is called a sine. So now you can see we can ask how this looks when you expand it to small for small phi. So you can see that, so u of phi is equal to m square by beta square into 1 minus cosine beta of phi, which is equal to 2 m square by beta square sine beta phi by 2 whole square, okay. So now you can see for small phi this this whole thing will become, this is equal to m square by 2 phi square plus nonlinear terms, okay. So now hopefully you can understand the joke. It is like saying taking the Klein-Gordon equation and replacing the mass term with the sign phi with sin phi, okay. So that is why it is called this thing. Okay. So, this is a model which is actually exactly solvable in many ways, okay. And so it's also a model which is called an integrable model in the strict classical field, classical mechanics sense, where you find that that it has an infinite number of conserved quantities in involution, etc., which is related to the fact that it's exactly solvable, okay. So in this model, now if you plot the potential, you can see that the potential u of phi, one more thing you can see here is there is a periodicity which is phi goes to phi plus 2 pi over beta. Okay. And so let me plot u of phi. So at phi equal to 0 it goes to 0, and then it sort of goes. So this would be at 0, and then first one would be 2 pi over beta, 4 pi over beta. And the maximum value will be when it is, this would be some 2 m square upon beta square. Okay. So now this is a case where you have many non degenerate degenerate vacua. You have infinite degeneracy. So the vacuum solution, let us call them phi n equal to whatever values it take when it becomes 0, that is just 2 pi over beta times n. Okay. So for any of these things you are at the minimum of the potential, okay. And obviously this has kink solutions which interpolate. So clearly, so this has kink solitons that interpolate between say phi n and phi n plus 1. Say. So this will be a kink, and anti kinks will go opposite. So this is the boundary condition at x equal to minus infinity, and it goes to this at x equal to plus infinity. So that is what I am using in this notation. So it can go from 1 phi n to phi n minus 1, any one of these things it could do, it interpolates between them, okay. But unlike so in the phi 4 theory there was a kink and an anti kink, but now I can have a situation where I have a solution which interpolates between 0 and 4 pi beta. So that we can, so you can think of that at least as for instance in phi 4 theory you could not put superpose two kink solutions because it will violate the boundary condition, but here you can. If you put two kinks together, it will take you from 0 to 2, first kink will take you from 0 to 2 pi over beta, and the next kink will take you from there, okay. So there are, so this thing has the usual kink solitons, or it has multi kink solutions. Okay. And so you could write a solution where the two kinks are fairly widely separated out. So you could write something like this. So just linear combination would work, okay. And so I am just plotting the energy density so that you can see it localized. But the point here is that, for instance, this is a two kink solution, you can write an exact two kink solution, you can solve it. More importantly, you could even say you could solve it for, this is localized here. So there is, it is at x1, this is localized at x2, let us say it has velocity v1 and this thing has velocity v2. You could write solutions which actually do all these things, and this is related to the fact that it is an integrable model. There is some nice structure which comes out, okay. So you have quite a bit of control. So you can ask what is the kink interaction, because you know all these things. So you take the kinks, you separate them and ask is there some what is the energy between them. You can work out lots of stuff, could do the dynamics of these things and write an effective potential between these things, So it's a so in that sense it's a very very malleable and ductile model. You can do all sorts of things to it. So just for completeness, I will just give you the kink solution, and let us do some little bit more things. So you can see that classically at least I can do the following thing. I can take phi beta phi and just call it phi. Okay. What I mean by that, if you are confused, you just say beta phi equal to phi tilde. You define it and then remove the tilde. Okay, that is what I mean by that. So what will happen here is that this beta phi will become a phi. Okay, nothing happens here, but here we have to write this will become a phi upon beta. So you get a 1 by beta square. So the Lagrangian, which originally had just phi and beta, just goes over to 1 by beta square times, which just depends on phi. Okay, and the beta square dependence just disappear, I mean goes away in some sense. Okay. So but it is useful to remember that the Lagrangian has a 1 upon, if you want to put back things, just remember that you put a 1 by beta square in. Okay. And we will also be looking at time independent solutions. So we could also, then one more thing you could see is that there is an m square floating around. So you can go to dimensionless, you can define y to be mx. Okay. And so in terms of these new phi and y, beta and m completely disappear from the theory. Okay. So if you want time dependent solutions also, you could do that. You could just say that time also scales that way, and then you perfectly fine, the m goes away. Okay. So if you are looking at solutions on these books, you may, in several books you will find that some people will set beta equal to 1, a few others will set beta and m equal to 1. So it's a little bit of a mess if you are looking for the solutions, but you can see from this you can actually put things back. Okay. So let me just write out the one soliton solution, and so I am just giving you a soliton which is localized this at this thing. So for this solution you can actually check that I think sine phi by 2 is becomes secant hyperbola m. Show this. This is a useful identity which you need to, and cos phi by 2 will be I think tan hyperbolic mx. Okay. And you can go ahead and replace x by x minus v x minus x naught minus vt divided by square root of 1 minus v square, like we did for the other kink soliton. It will still solve the equation. The energy of this thing turns out to be 8 pi square upon beta square into m. So dimensionally again, is it 8 pi square or 8 pi? No, it is just 8, not even 8, 8 no pi's. So this again a simple calculation will tell you this. Okay. So far it looks like one more model we are looking at, and for once I have gone away from the only model I knew, the potential, which is 5/4. So it looks like, yeah, yet another thing, but we'll see pretty soon that this model is equivalent to dual to something completely different. Okay. So this is what we have. The energy is this thing, but so you can also show that the energy of n kinks in general is greater than or equal to I will put mod n with negative n representing anti kinks. Okay. And explicit solutions are known. Okay. So this is with respect to the kinks, but here is the, so this is, we'll call this model A. So model B I have to give you a Lagrangian etc. It is called the massive theoretic model. Just one last thing I want to mention about this model is that this model classically, like I said, beta is not very important, but quantum mechanically it is, okay. And so then there is a value of beta square, it should be less than or equal to 8 pi for the quantum theory to have a ground state. Otherwise you can show that by some variational methods. For instance, Coleman shows that the ground state energy is unbounded, okay. So that there is a sense in which you require, so this is a quantum mechanical statement, this is not something which you can show classically. Classically we saw, right, it just goes off, it goes for the ride, okay. So the massive theoretic model is a model which has fermions, it is a model in 1+1 dimensions, and it is a model of fermions, and the Lagrangian has the following form. So some 2-dimensional Pauli matrices, the analog of, so this would give you a massless Dirac equation, okay. We have not discussed fermions, but it does not, for our purposes it is just to show you what is going on. And then it has a coupling which I will write out for you, it has 2 kinds of couplings. Okay, where J mu, so again you would have seen this in your relativistic quantum mechanics course. This is what would have coupled to electromagnetism, for instance, okay. And this is like a charge, this thing is just sigma is just psi bar psi, okay. So psi bar would correspond to psi dagger with some charge conjugation matrix. So usually you take it to be, depending on your convention, it is typically gamma 0, okay. So this, if you wish, in components, like in 4 dimensions, Dirac equation, Dirac fermions had 4 components. Here there will be 2, and roughly you can think of them as left and right movers, okay. So here is the remarkable claim. So now you can see that this is interactions, it has 4 psi bar J mu which is psi power 4. So it is like a 4 Fermi interaction. This is a mass term because it is quadratic in this thing, in the field. So it is exactly like the scalar fields, except there is little bit more stuff going with it. So this is the kind of what we will call a mass term, but actually this theory apparently does not have one particle excitation. So this you cannot think of this as mass of that thing, you just think of it as some parameter, okay. So it has 2 parameters, G and M tilde, and you can see that when G equal to 0, it is just a theory of a massive Dirac particle in 1+1 dimension, okay. So this is the model and claim model B is dual to model A. Kind of confusing, right? One is a theory which is a scalar theory, model A. So this is a theory which is fundamental excitations are fermions, and here is a mapping. The mapping is the following. Okay, I will explain all these things one by one, but the key point here is to look at first. Let us go look at the first term in this thing, which says that the coupling beta goes, it is like an inverse of this. So, small beta implies large G and vice versa. Okay. So this is exactly like that strong weak kind of stuff. Then this is kind of, this is also very, this is sort of gives you a hint about things. What it is telling you is that this is your this is the current which is usually conserved, but this is, like I said, the electromagnetic current. So it is another current corresponding to electromagnetic invariance, U1 global. Okay, that is another current for that in this theory. So on this side, but in this what is this one in the sine Gordon side, it is a topological current. So what is happening is that a topological current on one side is getting mapped to another current in the new variables. Okay, and so in fact you can see, you can show this n here is just beta. Is there a beta square here or a beta? Let me check that. It is just beta, yeah. This is just the topological charge, and the kink number, okay, is really that. Okay, and so this gives you a relationship between the two ends, if you wish. So it also tells you that the interaction, so the interactions of the sine Gordon theory get is this, yeah, in some sense this term gets mapped to this. That is about all I can say. But you can also see something interesting happen when beta square is 4 pi, which is below this limit. What happens? G becomes 0. Okay, so there is a point which is the, we will say, the free fermion point or the massive fermion point, which is beta square equal to 4 pi. Okay, so let us try to understand how this model actually captures this soliton, what I call the soliton and elementary particle democracy. Okay. So the idea here, so the thing is that the kink soliton of the sine Gordon theory actually is a fermion of the theoretic model. Okay, and the way it goes, the way, so this was shown by, in a very nice paper by Mandelstam. Okay, so whose idea was the following: suppose I have a kink localized out here at some point x naught. Okay, and so what is the, let us say that what this is doing is that it goes from 0 to, so it is a kink in the sense of it a soliton number 1, and so it just does this. So let us say it goes, so the configuration looks like this, it does something like this. Okay, so this is the energy density versus x, and this is here. So x naught is somewhere the location roughly of this thing. Okay, so so suppose you want to construct, so you want to construct an operator. So what Mandelstam does, he constructs, so if you want to destroy this kink, right, what you should do is you should at this point you should have something which will bring the roughly it should undo this. Okay, so he constructs an operator. Okay, this is non-local in the sine Gordon theory, okay, which has the following property. So let me just write that. So, phi is just the field. This is when y is less than x, and then okay. So, what it is doing here is on this side. So, this one is telling you, oh, is it, yeah, psi. So, this just tells you that this phi jumps, this commutation relation just tells you that this jumps by 2 pi by beta, which is what was really. So, this had to be 2 pi over beta, right, for a single kink. So, it creates a jump, okay, and so it so this is undoing this, okay, or if there was nothing, if it was acting on vacuum, it is changing it, okay. So, in that sense it has the same role as what the kink soliton was doing. Okay, so, he has to construct such an operator, okay, and he does, and it is non-local, as you will see, just as the disorder variable was non-local. So, so keep in mind that this psi which I am writing is completely written in this in the Sine-Gordon theory, and so it is a quantum operator. It requires normal ordering, just give me a second, I beta over 2. So, you can see it is a non-local object. First thing is it is exponential, and it is an integral from minus infinity to x. So, it is going from minus infinity to this point x, this became x naught here, okay. So, he constructs this and shows that it satisfies that, okay. So, you need I mean little bit of quantum field theory is needed, but you can, what I want you to get from here is that this is a non-local object, okay. And now once he has this thing, he needs to show that this so the thing among other things you would like to show is that this psi behaves like a fermion. So, its psi is anti-commute, and you should also show that you can recover it the interactions of the size are those of the Thirring model, the massive Thirring model, okay. So, he goes ahead and shows this thing, okay. So, this is very remarkable, and this kind of shows you how what was a soliton in one theory. So, for instance, I would think that if beta square is 4 pi, it is like okay, in some sense strong coupling, okay. That there I would say that it is probably better to think of describing that equation by the massive Thirring model with g equal to 0. It's probably a nicer simpler one to do it, okay. So, this is my second example where I want to show you how solitons in a theory can become the fundamental excitations of another theory, okay. So, are there any questions? How do you write that? Okay, so the easiest way is to use this. So, this gives you psi bar psi is d nu of psi. So, this is the way. So, in fact you can set g equal to 0 and m tilde equal to 0, it is a free fermion, free massless fermion. There is a method called bosonization which takes you from here to that, okay. And then this is the starting point. So, you can see that this is roughly tells you what how to go the other way. Yeah. Okay. So you might say, hey, this is a toy model and this may not represent reality. Yes and no, we will see a slightly. So, let us look at a model in 3+1 dimensions. So, we look at so the model will be so model will be, say, let us consider some okay. Let us consider for starters, let us just take SU2 Young-Mills. Okay. So, we have seen that this thing has a nice this thing has a coupling, it was what, 4 pi upon g square. So, I defined something called, I combined things like this. I wrote the coupling in this theory is given by this tau. Okay. So, the question is can we understand, is there an analog of electric magnetic duality okay, and if so, what does that look like? Okay. So, let us go back to electromagnetism E and M, and we know that there is a duality which does the following thing. It takes electric field to magnetic field, and magnetic field, I do not know, somewhere there has to be a minus sign. So, I am putting it out here. So, electric and magnetic fields get exchanged, and we wrote this in terms by saying that the role of F mu nu and F tilde mu nu are exchanged, which is the dual, are exchanged. Okay. And yeah, so but now if you remember, there was exactly the following thing is that the equation of motion, this was equal to 0, this was the equation of motion, but this was just a trivial identity. This was the one which lets you solve for F mu nu in terms of vector fields. So, this is an identity. Okay. So, this is without sources. Okay. So, now the thing is, now that suppose we had under electric and magnetic duality, you can see that the role of F and F tilde get exchanged, and what is happening is that you have, so this is a Bianchi identity. So, the Bianchi identity and the equations of motions roles get exchanged. In some sense, that is similar to what happened here. Another current is becoming, this is a trivial identity, this did not require equations of motion to solve it, but this required. Okay. Same thing is true out here, this is the equations of motion, this is does not require anything, it is just an identity. Okay. So, topological current, so in that sense it is similar to that. Okay. So, obviously I can just do the same thing, except for if you have some non-abelian gauge theory, I can always go ahead and exchange. I now, instead of working with these things, these would be adjoint valued objects, but both of them are adjoint valued, so I can exchange them. So, it is very clear, we can state, so the non-abelian electric magnetic duality okay, it is just F tilde mu nu being rather F okay, but actually it is not just that, it is also it corresponds to taking so let us say that theta, when theta is 0, at least let me write, let us put theta equal to 0, it takes it corresponds to taking 4 pi g square to the inverse of that. Sorry, let me redefine my tau in a slightly different manner. I think it is usually the real part, I exchange the real and imaginary. Okay. So this is so this actually has to be combined with this thing. So now you can see that electric magnetic duality, if you just look at this thing, small g is where perturbative things become this thing, but yeah, so the coupling constant being small in one side becomes coupling being larger on the other side. So it is again a strong weak thing. Another way of seeing it, if you go back and you look at the example of, we had worked out the monopole for SU2 cross U1, and if you remember, the mass of the monopole, okay, was very, it was heavy, right, it was, it went by it was divided by g square. So again it is exactly like the kink had a 1 by beta square, so it is the same thing which is happening out here. Okay. So but there is a nicer way of writing this thing. So when theta is not equal to 0, this is slightly more involved. I am not giving any proofs or anything, I am just writing these things out for you. Tau goes to minus 1 upon tau, and you can see that that will work out, because when theta is 0, the minus sign will get cancelled by the I going below, and then again it will work out, it will be exactly what I wrote. Okay. But there is another, so this is what we will call normal electric magnetic duality, but because we have a theta term, we have actually, so now theta comes, if you remember, the theta term comes out like this, right, times the incident on number, and quantum mechanically there is a equivalence, theta goes to theta over to theta plus 2 pi. So theta is a period, it is an angle variable, not a this thing. So theta is angle. So there is a second, so this is the first one, the second transformation is theta goes to theta plus 2 pi, but that is easier stated if you look here, that is, or tau goes to tau plus 1. Okay. So this looks like it does not change anything in the quantum mechanical story, and so but this is a symmetry of this theory. Okay. These two actually combine, these two symmetries combine and generate a group called SL2Z, which tau goes to A tau plus B over C tau plus D, and where this A, B, C, D are integer elements such that determinant of this is equal to plus 1. Yeah, there is a yes. So there is any trivial equivalence if all A, B, C, D are minus of themselves. So that is a Z2 orbit. So it is called technically PSL2Z, but okay. So one thing you can see here is that again, just going back to plain electric magnetic duality, what it tells you is that if you are going to the strong coupling limit, then probably if there are what you thought was I mean there could be monopoles which become very light and your electrically charged objects become heavy. So this tells you that what you thought was your electron in this thing, in this setup, would become a solitron in that theory, and vice versa. Okay. So there is this thing, but it also tells you, suppose you have a situation where both electric and magnetic there are things which ions become the lightest. Okay. Then you could be in a situation where actually there exists no local description. Okay. And there is a class of so so in these theories, so this is just I started out with normal SU2 Yang-Mills, but we could we know a little bit more when you add supersymmetry to this theory. So so whatever this means, n equal to 2 supersymmetric Yang-Mills. Okay, so this will have this, so this again will have this parameter tau, and the same things go through, but because there is supersymmetry in the problem, we find that we have a lot more control, and many of the so you can so for instance here the theory is determined uniquely by one function, okay. So it's some so we'll just say it's some function of something of some fields, and if you give me this function, I can write out for you the full Lagrangian for the theory. Okay, so it's determined completely because supersymmetry relates various terms. It relates bosonic terms to fermionic terms, and when there is a lot of supersymmetry, you will find that you can actually. So this prepotential, it's called the prepotential, it determines the Lagrangian. So if you take this kind of symmetry seriously, you can go ahead and you can ask, can we figure out this function which has this, which should have some properties. So in fact duality plus supersymmetry plus a little bit more, but okay, determine. So this f, you will start out writing your normal classical thing, but what you want is a quantum corrected this thing. So you can actually determine the quantum prepotential. Okay, and this is a tour de force due to Seiberg and Witten. I think around 1995. Okay, and so this is another non-trivial example where duality symmetries tell you expect this thing. So the thing is that consistency with these things and the fact that this has to be a certain kind of some analyticity properties more or less fix the form of this thing, and it turns out that this is determined by some other funny torus or whatever which comes into play, and this SL2Z, there is some torus which determines this completely. And so it's sort of this sort of an extreme case of a field theory, a quantum field theory being solved by just consistency in some sense. Okay, and taking the idea of soliton elementary particle democracy very seriously. So you look at the solitons in this theory, etc. Okay, so I am done for today.